either correct or not correct. Now that we've made the first round of predictions, we're prepared to make a few more. We predict reusable rockets will lower the cost of rocket launches by 30 to 50% in the next 20 years. We predict it will be possible to diagnose most cancers with a blood test in the next 30 years. We predict that nanobiomachines will cure most genetic disorders in the next 50 years. Okay, that's a total of 11 predictions. We believe that if we get 8 out of 11, we should be considered geniuses. Oh, and if any of the first set comes true, you can write clever news articles with titles like, "Couple who predicted the future of gene sequencing say spacefaring will be cheap in near future." Predicting the future accurately is hard. Really hard. New technologies are almost never the work of isolated geniuses with a neat idea. As time goes on, this is more and more true. A given future technology may need any number of intermediate technologies to develop beforehand, and many of them appear to be irrelevant when they are first discovered. One recently developed device we discuss in the book is called a superconducting quantum interference device, aka a SQUID. This very sensitive device detects subtle magnetic fields in the brain, which is one way to analyze people's thought patterns without drilling holes in their skulls. How did we get this thing? Well, a superconductor is any material that conducts electricity without losing any electricity on the way. This is different from a regular old conductor, like a copper wire, which transmits electricity pretty well, but loses some en route. We have superconductors because about 200 years ago, Michael Faraday was making some glassware and accidentally turned a gas into a liquid by trapping it under pressure in a glass tube. There wasn't TV back then, so a bunch of Victorians got really excited about the idea of liquefying gases. As it turns out, it's easier to liquefy gases by getting them really cold rather than getting them really pressurized. This insight led scientists to develop advanced refrigeration technology, which allowed them to liquefy stubbornly gassy elements like hydrogen and helium. And once you have liquid hydrogen or helium, you can use them to cool down just about anything you like. Helium, for example, is about negative 450 degrees Fahrenheit when in liquid form. If you pour it onto just about anything, the liquid helium turns into a gas and takes heat away with it, until the thing you're cooling is about negative 450 degrees. To understand why, think of it like pouring cold water on a hot pan. The pan transfers a bunch of its heat to the water and thus cools down. You can cool it down faster by pouring off the water and getting new cold water. That cold water is something like 50 degrees Fahrenheit, so you can keep cooling the pan until it gets down to 50 degrees Fahrenheit. After that, the water is the same temperature as the pan, so the heat can't just go from one thing to another. It'd be sort of like trying to dry off with a towel that's just as wet as you are. You can't get drier without a drier towel, and you can't get colder without a colder cooling liquid. Eventually, scientists wondered about what happens to conductors when you get them really cold. Conductors tend to get better at what they do as they cool down. In simple terms, this is because conductors are sort of like pipes for electrons, but they're not perfect. In a copper wire, for example, the copper atoms get in the way of electron motion. What we call heat is really just rapid wobbling at an atomic level. When you heat, aka wobble, atoms in copper wire, they are more likely to block electrons from moving downstream. In the same way, it's harder to get down the street if the guy in front of you keeps changing lanes over and over. At the level of atoms, wobbling, aka heat, means the electrons are more likely to bump into copper atoms, increasing the wobble still more. This is why your laptop charger gets really hot after you use it for a while. When you put that liquid helium on the conductor, the wobble energy in the copper atoms is transferred to the helium atoms, which then fly away. Now your copper atoms are less wobbly, and your electrons experience a lot less resistance. The colder they get, the easier it is for electrons to flow. Back then, there was a debate about what would happen when you got toward zero wobble. Some thought conductance would cease, because at that temperature, motion should be impossible, even for electrons. Some thought conductance would get very good, but nothing special would happen. So researchers started to pour their ultra-cold gases onto metal elements. It turned out, bizarrely, that some metals became perfect conductors, aka superconductors, when they reached a certain very low temperature. If you kept the metal cold enough to superconduct, you could put electric current in a loop and it would just keep looping forever. This may sound